Hello all. So in last class we have discussed about pure RLC circuit, behavior of pure resistor, pure inductor and pure capacitor with AC signals. So now today we are going to discuss about behavior of RL circuit, RC circuit and then combination of all three RLC circuit. So to start with, first let us consider RL circuit. So as you can see here in the figure shows a pure resistor R which is connected with a pure inductor L across an alternating voltage of V. So let V and I be the RMS values of the applied voltage in the current. Then the potential difference across the resistor will be given as VR equals to R into I, and the potential difference across the inductor will be given as VL equals to XL into I, right? So now if you are going to draw the phasor diagram, then the phasor diagram will contain two components of voltage which are called as VR and VL, and we have one current component. So let us consider the current component is fixed and given by this line, this phasor. Now as we already know, the value of VR or the VR phasor will be in phase with the current. So let us consider this is our VR, and also we know that the voltage across the inductor will be leading the current I by an angle 90 degree. So let us consider that it is given by this line which is at VL, which is at phase difference of 90 degree. Okay. So now what would be the actual difference between the voltage phasor and the current phasor will be the resultant of these two. So we will be having the resultant here. So this is the voltage which will be at an angle of, let us consider this to be phi. Okay, so this is the phasor diagram for series RL circuit. Now from this diagram we can also draw the voltage triangle which will be given by so this is the voltage triangle where we have, this is the resultant voltage, this is the voltage across inductor, and this is the voltage across resistor. Okay, and the angle between them is given by phi. So this represents the voltage triangle. So from this, if you determine the value of cos phi, which is the power factor, will be nothing but VR divided by V. Okay, so this is the phasor diagram and the corresponding voltage triangle for RL circuit. Okay, so now let us move for the impedance. So the impedance, to determine the impedance, we already have V equals to VR plus VL, right? Now this can be written as VR is Ri and VL is J of XL into I. Now if I take I common, it will be R plus J XL, right? Now what is Z? Z is nothing but V by I, which is equals to R plus J XL, right? So now so now from this we can have the magnitude of Z will be given as R square plus XL square, and XL is nothing but omega L, so we can write it like this. And similarly the angle will be equals to tan inverse of XL by R, which is omega L by R. Now like the voltage triangle, we can also have the impedance triangle, which will be the triangles will be same, and this is the component due to resistance, this is the component due to inductance, and the resultant is Z. So this is the impedance triangle. And from here also we can determine the value of power factor. So cos phi is given by R by Z. Okay. So now moving on to the other components. So first is current. So what will be the current? As we already know, the value of voltage is V equals to Vm of sin omega t. Since the current is at the phasor difference of phi, so we can write it as I equals to Im sin of, since current is lagging, so it will be omega t minus phi, right, where Im is given by Vm by Z. Okay, and the angle is, we have already determined, which is tan inverse of omega L by R. Okay, so now moving on to the waveform. So the waveform will be, if this is the value of voltage, or this is the waveform for voltage, voltage is at Vm, we already know, so if this is the voltage, then current will lag by an angle phi. So this value is phi. This is the waveform for current, right? Hope you have understood. Now let us move into the other components, which is power. So the power will be given as P equals to V into I. Now the voltage is Vm sin of omega t, and the current is Im sin of omega t minus phi. Now this can also be written as Vm Im, and here this sin omega t and sin omega t minus phi can be considered as sin A sin B, so which also can be written as cos phi, that means the addition and subtraction of cos angles, so omega t minus phi divided by 2. So this can be simplified as Vm Im divided by 2, this is cos phi, then minus Vm Im divided by 2 cos of 2 omega t minus phi. Now here we have this component as a fixed value, right? Since we have a fixed value for the phi, and this Vm Im are also fixed values, so that is why this is the constant term. So this is the constant term, and this term represents a fluctuating component, so which is already defined because we are dealing with resistance and inductance, and due to resistor we must have a constant term, so this is the that constant term, and due to inductor we should also have a fluctuating term, so this is the fluctuating term. So if you go to determine the average power, then the average power will be P equals to Vm Im divided by 2 cos of phi. Now this can also be written as Vm root 2 Im divided by root 2 cos of phi, which is known as Vi cos phi. So this power is also known as active power. This power is also known as active power. So P equals to Vi cos phi. Okay, then if you determine the unit, then this unit will be in watt. Next is, from the reactive component we have another component which is known as reactive power. So that will be given by Q Vi sin phi, and the unit here is volt ampere reactive. Okay, then these two are the components. So if we draw the power triangle similarly to voltage triangle and impedance triangle, if we draw the power triangle, then we have the resistance component is active power, we have the inductive component as the reactive power, and the resultant should be called as apparent power. So the apparent power is given by S equals to root over P square plus Q square, right, as per this. So we have our power triangle now. So from here also we can determine the values of the power factor, which I have to determine next. So these values now can also be written as, let me use another color. So Vi cos phi, here we have for V we can write it as Z into I, then cos phi is R by Z from the impedance triangle. So here Z will get cancelled, this is I square R. Then next for reactive power it will be Z I, and this is XL by Z, so this will be I square XL, right, and then apparent power will be equals to Z I, so which is I square Z, right. So these are active power, reactive power and apparent power. Now the power factor, which we have already determined in case of the voltage triangle, the power factor is VR by V. In case of impedance triangle, the power factor is given as R by Z. Then from power triangle it is given as P by S. Okay, so this is the derivation for RL circuit. Okay, so I hope you have understood this. So now let us move to the RC circuit. So similar to RL circuit, we also have RC circuit. Here we have the resistance is connected with a pure capacitor. So now here the potential difference across the resistor will be VR equals to R into I. Here VC equals to XC into I. The phasor diagram will be so now here we have current as common, so this is current. Then we have VR, so this is VR, and we already know VC lags current by 90 degree, so this is VC, so this is the resultant, right. So this is the phasor diagram. Now from this, if you draw the voltage triangle, then it will be like this. So this will be the voltage triangle. This is the angle phi. So here we have cos phi as VR by phi. So like this we can also determine the remaining values for current waveform, power and average power. Impedance, so impedance would be V equals to VR plus VC. So here VR is R into I, then VC is V times of XC into I. Now here taking I common, we have R minus AXC, so Z equals to, we already know V by I, so which is R minus AXC, and so the magnitude will be given by R square plus XC square, and the angle will be tan inverse of XC by R. So this XC is also known as, or also we have determined in our earlier classes that the value of XC is 1 by omega C. So the so the angle will be tan inverse of 1 by omega CR. So for current, we already know V equals to Vm sin omega t, and in this case the current leads the voltage by an angle phi, so it will be Im sin of omega t plus phi. So where we have Im value is given as omega m divided by z, and where the angle phi is given as, we have already determined, tan inverse of XC by R, or equals to tan inverse of 1 by omega RC. So this is the value of current. So now if we draw the waveform, so let us draw the waveform here. So now here what we have is, we have current leading and voltage lagging. So if I draw this as the current, then the voltage will be starting after phi. This value is phi. The phase difference is phi. So similarly, like in earlier case, the power will be active power, which will be given as Vi cos phi, which is I square R. Then comes reactive power, and reactive power is Vi sin phi, which is I square XC. And we have the apparent power, which is given as Vi, which is equals to I square Z, right? So if we draw the power triangle and the impedance triangle, then it will be like this. This is the angle phi. So let me make a copy of this. Okay. So next let us draw for the power triangle. These are the angle phi. So this is resistance, this is reactance, this is the value of Z, impedance, and here we have active power, reactive power and apparent power. So this is the impedance triangle. This is the impedance triangle, and this is the power triangle, right? So the power factor is, as we know, the power factor in case of the voltage triangle, it is VR by V. So let me write it below. So the power factor due to the voltage triangle is VR by V. Power factor due to the impedance triangle is R by Z, and the power factor of the power triangle is given by P by S. Okay, So this is the case of RC circuit. So now we have found out the derivation for RL and RC circuit. Now if we consider the or continue the same for RLC circuit, then we will have 3 different conditions. So what are those? To know that, first let us see the diagram. So this is the circuit diagram for RLC circuit, where we have pure resistor, pure inductor and pure capacitor, and applied by a voltage V, and the current in the circuit is I. So the potential difference across the resistor, as we already know, VR is Ri, then VL is XLI, and VC is XCI. Now whenever we are going to draw the phasor diagram, then we already have the common component I, and here we have the resistance component, which is VR, and we have inductor component VL, and we have the capacitive component VC. Okay, so now depending on the value of VL and VC, there can be 3 conditions. So first condition can be if VL is greater than VC. If that is the case, then it will be similar to the inductor circuit. That means Y inductor circuit. As you can see here, if VL is greater than VC, then this line will be smaller. So let me put another color for understanding. So suppose white. So if this is the case, then this may be VC. If this is VC, then combination of VL and VC will we will have to deduct the amount of VC from VL, so it will be somewhere around here. So finally the diagram will be like this, and this is your VL minus VC, and this will be the resultant. So now this is nothing but representation of a RL circuit, right? So if VL is greater than VC, it will correspond to the RL circuit, where we have this is VL minus VC, and this is VR, and this is your V, right? So now this is I, this is VR, right? So now next condition could be if VL is less than VC. So this will be opposite to whatever we have just considered now. So now the value of VC will be longer, or the vector VC will be longer than the VL. So after subtracting, we will have the phasor like this. This is I, this is VR, and this will be combination of VL and VC. So it will be VC minus VL. Then the resultant will be like this. So which is nothing but resembling the RC circuit, right? So remaining every condition, every derivation will be same as RC circuit, and this will be similar to RL circuit. So as we have discussed already, the derivation or what would be the response for RL circuit and RC circuit, so it will continue as it is. So I hope we can continue from here itself. Now the third condition could be if VL equals to VC. Now this is something new. Now if VL is equals to VC, then they will cancel each other. That means if this is I, then VL and VC will cancel each other, and what remains is VR only. Okay, and this condition, when VC equals to VL, is known as resonance. So in resonance, we have both the components VL and VC are same. So the resultant is similar to the resistive circuit. So the derivation will follow the resistive component calculations, right? So for this circuit diagram for the series RLC circuit, what we have to do is we have to consider three conditions. The conditions are, this is case 1 when VL is greater than VC, then this is case 2 where we have VL less than VC, and we have a case 3 of VL equals to VC. So you just continue for these two, first case and second case, and for the third case when VL equals to VC, we will see the derivation in our next class. So where we will be discussing the resonance circuits. So resonance circuit means the series and parallel resonance, and we will also find out what is the bandwidth at resonance. So with this, let us wind up here. So I hope you have understood this. So in the next class we will be continuing with resonance, and then we will be doing some numericals on this topic, whatever we have discussed. Thank you all. Thank you for joining.